In this video, I'm going to go over the concept of converting a Fischer projection into a Haworth projection. So for this first example here, we have this Fischer projection, and let's say we want to convert this Fischer projection into a six-membered ring in the Haworth projection. So we know that this CHO group here represents an aldehyde, so I'm going to redraw that to make it look more clear as an aldehyde, where that's going to be the carbon, and let's say this is the carbonyl with the hydrogen there. So this is the CHO. Okay, so we know that this carbonyl carbon of the aldehyde is the electrophilic carbon where a nucleophile attacks. So I'm going to number that as our atom number 1. So this is going to be number 1. And since we said that we are going to make a six-membered ring, I'm going to count downwards where we are going to reach our sixth atom, which has to be nucleophilic, because that nucleophile atom is going to attack this electrophilic carbonyl carbon. So counting down, we have 1, 2, 3, 4, 5. If we keep going down here, that is going to be a carbon, which is not nucleophilic enough to attack that carbonyl carbon. But we see that to the right of number 5, we see a nucleophilic oxygen. But in that case, the numbering is not where we want it to go down, so we have to do some rotation here. So I'm going to rotate these 3 groups here and keep everything on the top stationary. So I'm going to move the OH group down there, the CH2OH group over there, and then the hydrogen group to the right side. Redrawing everything, we are going to get this Fischer projection here. Okay, so now this is the new rotated Fischer projection we have, which is the same thing, but now if we count down from the electrophilic carbonyl carbon down to carbon or the atom 6, we see that our atom 6 is the nucleophilic oxygen which we want. So from here, I imagine this vertical line of the Fischer projection as my arm, and I'm going to flip it down to the right. So I'm going to flip all of this group down to the right here, which will give me this Fischer projection here. So in this case, we flipped everything to the right, where this is our carbon 1 and this is our atom 6 there. And this is our carbon 2, 3, 4, 5, 6. So let's focus specifically on carbon 2. We see that the hydroxyl group is on the right side, and imagine that this is our hydroxyl group on the right side here. If we flip our right hand to the right side like that, we see that the hydroxyl group is facing downwards. So I'm going to place the hydroxyl group facing downwards here, and we notice that the hydrogen on the carbon 2 is on the left side. So let's say this is the hydrogen here. If we flip the arm to the right side, the hydrogen is going to be facing upwards. So the hydrogen is going to face upwards here. So we're going to do the same thing for the other carbons. Carbon 3, the hydroxyl group is on the left side, meaning that it is going to face upwards. Carbon 4 is the same as carbon 2. Carbon 5, we see the CH2OH is facing on the left side, which means that when we flip it, the CH2OH is going to be facing upwards. So I'm going to draw the CH2OH as this bond line form here to save more space, and the hydrogen on the bottom here. Okay? So from here, I'm going to use the lone pairs of oxygen here to attack this carbonyl carbon and kick up the carbonyl bond onto the oxygen here. We know that this carbonyl carbon is sp2 flat, which means that this hydroxyl group attacking that carbonyl carbon can either attack on the top side or the bottom side, which is why this carbonyl carbon is referred to as the anomeric carbon. Okay. So after this reaction, we are going to get this Haworth projection here, where we see our atom 6 is the oxygen, where it just gets deprotonated by some kind of base to be neutral. At carbon 1, we have, let's say, squiggly line OH, because the carbonyl oxygen could be the top or bottom side, and carbon 2, the OH is going to face downwards. Carbon 3, we see the OH is going upwards. Carbon 4, the OH is going downwards. Carbon 5, the CH2OH is going upwards here. So that's how we convert the Fischer projection to the Haworth projection for an aldose. But now let's go over an example of a ketose here. In the ketose case, we could form two types of rings, a 5-membered ring or a 6-membered ring. So let's say we wanted to form a 5-membered ring. We are just going to start with the carbonyl-carbon, which is electrophilic, and go down to reach our nucleophilic atom number 5. Since this carbon here is not nucleophilic enough, our nucleophilic atom would be the oxygen on the right side. So we just repeat the process as previously. We are going to rotate these 3 groups like that and repeat the process. But let's say we wanted to form a 6-membered ring instead. Then we could keep going downwards, where our 6th atom is going to be this nucleophilic oxygen, which we could just redraw this CH2OH as this here, where if we go down, then our 6th atom is the nucleophilic oxygen, and then we could just flip that vertical arm to the right without doing any rotation. And that should give us our 6-membered Haworth projection.